phone. We were late. Maybe we can start now. Your mic is mute. Xiaoyue, your mic is mute.
Sorry. This semester we focused on the representations of SL3 and to research the highest weight theorem on it. And before we start, we introduce these notations. H1, H2, and XY, they are the basis of SL3. And this is the corresponding roots and root vectors. We define the simple roots as alpha1 and alpha2. We say if pi is a representation of SL3, then an ordered pair mu is defined as a weight for pi. If there exists a non-zero vector v such that it is the eigenvector of H1 and H2. And such a vector, we called it as a weight vector. And the space of all vectors constitutes the weight space corresponding to the eigenvalue mu. This lemma says if alpha is a root of SL3 and Z alpha is a root vector corresponding to alpha, then if we apply Z alpha to the root vector, we can obtain a new modified weight is mu plus alpha if the action on V is not equal to 0. To prove this lemma, we use the commuting relations in Lie algebra and substitute the relations in this equation. Then we can obtain the results. Now we can define the highest weight. We say if we have two weights, mu1 and mu2, for the representation of SL3, then we define mu1 is higher than mu2 if the subtraction can be expressed as A alpha1 plus B alpha2, and the alpha1 and the alpha2 are the defined simple roots. If AB, they or positive integer, then we say mu1 is higher than mu2. And so under this definition, we define a weight mu0 is a highest weight if all weights in this representation mu0 larger than mu. Then we can define the lowering operator pi z if it acts on a weight vector and if it shifts the vector to a lower vector or annihilates it to 0, then we say the z is the lowering operator. This is a lemma to prove the later theorem. And this lemma says if pi is a finite dimensional representation and H is a Cartesian subalgebra, suppose mu1 and 2 mu m are distinct weights for pi, then if V1 and Vm are elements of the corresponding weight space, the first point is if the sum of these vectors vanishes, which means if they equal to 0, then for all Vj, they must equal to 0. And the second point says if the sum is a non-zero weight vector with weight mu, then the weight vector must be the Vj, and the weight is what we have known, this mu1 to mu_m. The next lemma says every finite dimensional representation of SL3 possesses at least one weight. Then we can prove the weight space decomposition theorem. The theorem says if every irreducible representation of SL3, the operators pi1, h1, and h2 can be simultaneously diagonized. That it says V is the direct sum of its weight space. Firstly, we define W is the sum of the weight space in V. Since we have introduced that every finite dimensional representation of SL3 has at least one weight, so W must not a empty set. So if Z alpha is a root vector corresponding to root alpha, the action maps the weight space corresponding to mu into the weight space corresponding to mu plus alpha if the action on it is not equal to 0. Also from definition of weight space, W is also a invariant subspace under the action of H1 and H2. Then we know W is invariant under all of SL3 since it is a irreducible representation, so W must equal to V. And for the direct sum, we know that weight vectors with distinct weights are linearly independent, so V is actually can be expressed as the direct sum of its weight space. And a global basis for V can be constructed by choosing a local basis within each individual weight space and taking their union. Under this chosen basis, every basis vector constitutes a simultaneous eigenvector for H1 and H2. So which means they satisfy the definition of simultaneous diagonalization. Next, we define the highest weight cyclic representation. If a finite dimensional representation with weight mu, if it exists a non-zero vector, satisfies it is a eigenvector of Hi for all Hi in Cartesian subalgebra with weight mu. And the second, if it is annihilated by all Racine operators. And the smallest invariant subspace of V containing V is the entire space. The next lemma says if S is a non-empty finite partially ordered set, then S contains at least one maximal element. From this lemma, we know that SL3 is a finite dimensional complex semi-simple Lie algebra. So the sets of weights for any finite dimensional representation forms a finite poset. From this lemma, we know that a maximal weight mu always exists, and it ensures the existence of V. Next lemma is about reordering lemma. Firstly, we suppose G is any Lie algebra and pi is a representation of G. Let A1 to AM be an ordered basis for G as a vector space, then any expression of this form can be expressed as a linear combination of terms in the ordered form. We prove this lemma by mathematical inductions, and the base case is trivially it holds trivially, since a single factor is already in its ordered form. Then we assume the assertion holds for at most n factors. Now we consider an expression with n plus 1 factors. For the trailing n factors, we can order by our assumptions. So we can write it as aj, and the rest is in an ordered. Then we permute aj and ak by using the commutation relation. Since aj, ak can be expressed as this equation, and the last term we can express as the linear combination of ai, since ai is a basis. Then for the last term, since it has n terms, we can use our assumptions to say that this term must be in order. And for the first ordered, we can commute them successfully. Then we proved this lemma. Next theorem says if pi is a highest weight cyclic representation of SL3 with weight mu, then the representation pi has highest weight mu, and the weight space corresponding to mu is one-dimensional. We prove this theorem by reordering lemma. Let V be the weight vector with mu by definition of highest weight cyclic representation. Consider a subspace W spanned by elements of the lowering operator's action on V. We claim that W is an invariant subspace under SL3. We can prove the invariant property by this. We know that any basis action on W can be rearranged into the order in the orders. And since pi x v equal to 0 and H action act on V is scalars, so leaving only Y operators on V. So we say W is a non-zero invariant subspace containing V. And since each application of Y shifts the weights by minus alpha, and this is a simple root, for any generated basis vectors W, we can obtain the weights as this form, and then we can compare it with the vector V. So we can know that V is the highest weight vector, and mu is the corresponding highest weight. And then since the only elements in V can possess the weight mu is in the cases n equal to 0. So we say the dimension of weight space V mu is 1. And this lemma says every finite dimensional irreducible representation of SL3 is a highest weight cyclic representation with a unique highest weight mu. Let pi be a finite dimensional irreducible representation. Then we know that there must exist at least one maximal weight. For any non-zero weight vector V in the weight space, its maximum multiforces, and when X act on it, it must equal to 0. Since V is irreducible, the smallest invariant subspace containing V must be the entire space V. So pi is strictly highest weight cyclic. And then for the uniqueness, suppose we admit two distinct highest weights, mu1 and mu2, with non-zero highest weight vectors v1 and v2. Firstly, we define a subspace u1 equal to the span of y have action on v1. In this view, we know that every weight lambda in V must satisfy lambda must less than mu1. Since mu2 is a weight in V, so mu1 is not equal to mu2. And so we have mu2 must less than mu1. And for u2 is the same statement. We can obtain mu1 less than mu2. So the relations implies mu1 must equal to mu2. So the highest weight mu must be unique. Last definition says the completely reducible. We say a representation of a Lie algebra is that is completely reducible if the space V can be written as an internal direct sum of finite number of irreducible invariant subspace. And the next lemma says, suppose pi is a completely reducible representation of SL3 that is also a highest weight cyclic representation, then pi must be irreducible. Suppose pi is a completely reducible representation that is also highest weight cyclic with highest weight mu, and let V in VB is corresponding weight vectors. By assumption, we know that V can be decomposed into the direct sum of Vj. Since Vj is irreducible, from previous theorem, we know that it can be decomposed into the direct sum of its own weight space. So since mu is the highest weight, so there must exist a V0 such that V is in V0. And due to the definition of highest weight cyclic representation, and the Vj0 is irreducible invariant subspace, we know that Vj0 must equal to V. The next theorem, while theorem says if pi is a finite dimensional representation of a semi-simple Lie algebra G, then pi must be completely reducible. Next, we define the intertwining map. If there exists two representations, pi v and pi w, of a Lie algebra G, and a linear transformation phi v say it is an intertwining map if for all x in Lie algebra and v in the vector space satisfy this relation. Next, we introduce Schur's lemma. Let V and W be irreducible real or complex representation of a group or Lie algebra, and let phi is an intertwining map from V to W. Then either phi equal to 0 or it is an isomorphism. The next lemma says if V is a completely reducible representation of a Lie algebra, then every invariant subspace of V is also completely reducible. The definition of representation isomorphism says pi V and pi W are two representations of Lie algebra. Then a linear transformation is defined as a representation isomorphism if phi is a bijection and it is also an intertwining map.
I think you need to end soon because we got quite Q&A section also.
This theorem says two Two irreducible representation of SL3 with the same highest weights mu are isomorphism. We prove it by constructing the direct sum representation. Let U be the smallest invariant subspace containing the vector V and W. The joint action, we know from the joint action, U is a highest weight cyclic representation with highest weight mu. Since both V and W are irreducible, the direct sum of them is completely reducible. Because U is an invariant subspace inside a completely reducible environment, so it must be also completely reducible. With the condition of U is a highest weight cyclic representation, we can conclude that U is an irreducible representation. And then we consider the canonic projection maps P1 and P2. Since P1 and P2 are intertwining maps, their restrictions to the invariant subspace U denoted as P1 restriction on U and P2 remains intertwining maps. And since V and W are non-zero, we know that the maps is also non-zero. By Schumann lemmas, since U, W, and V are all irreducible and the maps are non-zero, so they must be isomorphism. So U is isomorphism to V and U is also isomorphism to W. So by the transitive, we know that V is isomorphism to W. The next definition is integral element and dominant. Integral element is defined as a element in complex plane M1 and M2 is integer, and dominant is if they larger than 0. This lemma says pi is an irreducible representation, and there exists a non-negative integral m such that the action h, y, x on a root, they satisfy these relations. And last lemma says pi is a representation of SL2, then every eigenvalue lambda of H is an integer, and if V is in this vector space, satisfies if V is a eigenvector of pi or pi H, then and x act on V is equal to 0, then lambda is a positive integer, non-negative integer. I think the proof can be skipped. And the last theorem says if pi is an irreducible representation with highest weight mu, then M1 and M2 are non-negative integers. We prove it by the definition. We know that x1 act on V is equal to 0, and this h1 V equal to M1 V. Consider the subalgebra as alpha 1 is constructed by h1, x1, and y1. Under this restriction, we know V is an highest weight vector with weight M1. So from the last lemma, we know M1 is a non-negative integer, and the same statement for alpha for M2. So from the two construction, we know mu must be a non-negative integers. The next definition is about standard representation. It defined as map X to X itself. And this example says the standard representation is a irreducible representation with highest weights 1, 0. The next definition is about dual representation. With respect to the standard representation, and it gives by the minus pi x and then transpose on it. This example says the dual representation of the standard representation is an irreducible representation with highest weight 0 and 1 and highest weight vector E3. E1, E2, E3 is the dual basis corresponding to the standard basis. So, and we know that they satisfy this relation. So under the dual action, the diagonal Cartan elements H1 and H2 have these relations. Then we can evaluate the weights of the dual basis vectors. We can know these three relations, and then we can define beta 1, beta 2, and beta 3. Find these roots, and we know beta 3 larger than beta 2 larger than beta 1. Sorry, this is weights. And we rewriting the basis as F1, F2, and F3, let them satisfying these relations, and then we can prove the descending operators Y1 in standard representation are descending operators in the dual representation. Then with these relations and the same method of proof in standard representation, we know W is the smallest invariant subspace containing F1. So we can prove this statement. The next definition is tensor product representation.
Can we wrap up because we are over time now? Can you wrap up?
Okay.
Yeah, because we are over time now.
就是
sorry.
翻页们，just
wrap up, finish off， 因为我们迟了 we are late.
Okay.
Yeah,
好。
别人的时间。
Okay.
There are some others need to start.
It's okay. Gio isn't here yet, so why don't you present the last
okay.
idea that you have? Yeah, just present the last thing that you have. You don't have to talk about the details, but just present the very last, or the main idea in the remaining slides. Just one more idea.
Okay.
So yeah, just one more idea. What's your main thing? Yes.
Okay. So the next the core theorem is say for any pair of non-negative integers, there exists a finite irreducible representation with highest weight, and we can prove it. Firstly, for the non-zero weights, for the zero weights, we know there must exist a trivial representation can fit the condition. And for at least one mi is not equal to 0, we construct the tensor product representation by the standard representation and dual representation. Is like that, then we can verify that this vector is the weight vector with weight m1 and m2, and then we can prove that E1 and E3 they are annihilated by all reason operators. So M1, M2 is also annihilated by the reason operators. Then we define W is the smallest invariant subspace containing the highest weights. So the restriction is a highest weight cyclic representation. Then if the next work is to prove pi M1, M2 restriction on V is completely reducible. then we can prove it is irreducible. And the remaining proof is about the unitary matrix. It can be found in the textbook. Then all is done. Thank you.
Okay.
Any comment or question?
Why don't you just show me the graph that you have. That's all I'll ask for you to. You have a graph. Can you just very briefly say what this is?
Oh, this graph, it says, it is an example of constructing the highest weight 1, 1. From the statements, we know that this E1 F1 is a tensor product, and the F1 is what we defined in the dual representations example, and the left branch is applied we constructed the tensor product representation pi 1, 1. The Y1 is action on it, then we produce a new weight vector. And the right is the action of Y2. So we can obtain the whole space, the whole representation.
Okay, yeah, no other questions. Thanks. Thank you very much.
Okay,
Thank you.
Thank you.
Bye-bye.